this lecture, we'll just work a few problems to illustrate how the gas laws are used. So there's 6 main equations. All right, you have P1V1 equals P2V2, Boyle's law. PT, total pressure, is the sum of the individual pressures of all of the gases. That's Dalton's law of partial pressures. V1 over T1 equals V2 over T2, Charles's law. Guy-Lussac's law, P1 over T1 equals P2 over T2. The ideal gas equation, PV equals nRT. And in calculating the molecular speed of a gas, mu is the square root of 3 RT over the m sub m, means molar mass. So those are the 6 equations. You just basically have to know how to use them in this chapter. So let's work a few problems. And so one of the goals will be to figure out which equation obviously that you need, and then simply use the equation. Okay, so first problem, a helium balloon at 789 millimeters of mercury and 23 degrees Celsius occupies 2.68 liters. What volume will it occupy at a pressure of 623 millimeters of mercury and 23 degrees Celsius? Okay, so what are you given? So you're given P1, you're given T1, and you're given V1, and then you're given also P2, and you're given T2, but if you notice T2 equals T1, so temperature is a constant. So basically you're given pressure and volume, and temperature is a constant, so probably you don't necessarily need it in this in this problem. So what equation relates pressure and volume? So that's going to be Boyle's law. So you just need P1V1 equals P2V2. And you're asked to solve for what volume will it occupy at the new pressure. So you're asked to solve for V2. So just rearrange this equation to solve for V2 is equal to P1V1 over P2. And then plug in the values and solve. So V2 equals P1, so 789 millimeters of mercury, times V1, 2.68 liters. So before we do the math, so let's see. So pressure is going down. So what should happen to volume? So if you remember, pressure and volume are inversely proportional to each other. So if pressure goes down, volume goes up. So if the new volume that you calculate is not bigger than what you started with, then obviously you got the problem wrong. So you can qualitatively check your answer that way if you know the relationship between pressure and volume. Okay, so plug in P2 is 623 millimeters of mercury. And then pressure cancels, millimeters of mercury cancel, and the only unit left is volume. So again, that's another way to check your answer. If you end up in the right unit, you probably got the answer right. Okay, so if you do the math, then you should get 3.35 liters. So the volume 2 is bigger than volume 1. So again, that's another qualitative way to check your answer to make sure that you did the math right. Okay, so number 2, a mole of gas. So you're given N1. The amount of moles at 0 degrees Celsius, you're given T1, and a pressure of 760 millimeters of mercury, so you're given P1. Occupies a volume 22.41 liters, so you're given V1. So what is the volume of the gas? So basically you want to solve for V2. At 20 degrees Celsius, you're given T2, and 760 millimeters of mercury, so you're given P2. But if you notice, P2 is the same as P1, so pressure cancels out. So, and the question doesn't say anything else about the amount of gas, so the moles of gas must be a constant as well. So the amount of gas is not changing. So the only thing changing is volume and temperature. So what equation relates volume and temperature? It's going to be Charles's law. So you need V1 over T1 equals V2 over T2. And so you're asked for the new volume, so solve this for V2. So V2 equals V1 T2 over T1. and then plug in values and solve. So a common mistake students would make, they would say, okay, V1 is 22.41 liters. T2, they would say is 20 degrees Celsius, and T1 is 0 degrees Celsius, and then try to solve that. Well, there's a couple of problems here. First of all, you can't divide by 0. But the second of all, you have to remember to use this equation, you must convert temperature to kelvins, or you can't do the math, or you're going to get the wrong answer. In this case, you can't even do the math because you can't divide by 0. Okay, so if we convert these temperatures to Kelvin, so V2 equals, so if you remember how to convert to Kelvin, you just add 273. So V1, 22.41 liters times, so 20 degrees Celsius plus 273, so 293 Kelvin. And then over 273 Kelvin. But again, before you even do the math, you can qualitatively think about the answer. So let's see, temperature is going up. So what should happen to volume? So if you know the relationship between temperature and volume, as temperature goes up, volume goes up. So the new volume that you can calculate better be bigger than what you started with, otherwise you know you did the math wrong. Okay, so if you multiply this out, you get 24.1 liters. So V2 is bigger than V1, which you know it should be since temperature is going up. And of course, Kelvin cancels. So you end up with the unit of liters. So your unit is right. Qualitatively, you know the volume should go up, so you can be pretty confident that you got the right answer. Okay, so what is the density of oxygen gas in grams per liter at 25 degrees Celsius and 0.85 atmosphere? So you're given temperature, you're given pressure, and let's see, indirectly you're given volume. Because question says what is density in grams per liter, basically, which means 1 liter. So volume is equal to 1 liter. Okay, so you have a temperature, you have a pressure, you have a volume, and then directly you have, so what equation is going to relate all of these? Oh, sorry, there was another equation here that I didn't write. P1 V1 over T1 equals P2 V2 over T2, the combined gas law. So you're given a pressure, volume, and temperature, but that's not the equation that you need because pressure, volume, and temperature is not changing. That's all constant. So what other equation has pressure, volume, and temperature in it would be the ideal gas law. So you're given pressure, you're given temperature, you're given volume, R is a constant. So if you can solve for N, so you can, let's see, so you can use those to solve for N. Okay, so first of all, let's convert temperature to Kelvin. So 25 degrees Celsius is going to be 298 Kelvin. And then use the ideal gas law, PV equals nRT. So let's solve for N. N is moles. Because if you solve for moles, then you can convert to grams, right? Using molar mass. And then once you have grams, you can divide it by the volume to get the density in grams per liters. So N is equal to PV over RT. So 0.85 atmosphere times 1 liter over R's 0.0821 liters atmosphere per mole Kelvin. And temperature 298 Kelvin. And your units, so let's see, so atmosphere on top cancels atmosphere on bottom. Kelvin cancels out, liters cancel out, and your only unit left is moles on the bottom of the bottom, which is the same as on the top. So if you calculate that out, then you get the moles of O2, which is 0.0347 mole of O2, and now you can convert that to grams. So just use the periodic table to calculate the molar mass of oxygen, of O2. So that gives you 1.1 grams of O2. So the density then is 1.11 grams per 1 liter. Okay, so that one's obviously a little bit harder than the first two. And then this one's number 4 is harder than the first 3. Okay, so lithium hydroxide is used in spacecraft to recondition the air. So according to this equation, so lithium hydroxide reacts with CO2 to make Li2O3. What's the name of that? So that would be lithium carbonate and water. So this is an important reaction in spacecraft. So what does it mean to recondition the air? Or where does the CO2 come from? That comes from the astronauts, of course, breathing. Every time they breathe oxygen in, they exhale CO2. And so if you're in space, then you have to deal with the CO2 that's exhaled from astronauts, right? So you got one of two ways in space to deal with it. You could either vent it to space, but that's not a very useful thing to do, because if you vent, because when you go into space, whatever you take with you is what you have, right? You can't run down to Walmart and get something else. So anything that you vent to space is just gone forever, and you're basically losing a resource. And so in this case, this is a useful reaction because, number one, you can diminish the amount of CO2 in the air so the air doesn't become toxic to breathe. And what's another reason why this is useful is this reaction generates H2O, water, which is obviously useful to have in space as well, because if you can make your own water, then you don't have to take it with you. Okay, so this is a reaction that's used. So in space, so question asks, so what volume of CO2? So that's basically what we want to solve for. At 21 degrees Celsius, so we're given a temperature, and 781 millimeters of mercury, so we're given a pressure, could be absorbed by 327 grams of lithium hydroxide. So if we have grams, we can always convert to moles. So basically we're given T, P, and N, and asked to solve for V, but we're given moles of lithium hydroxide. And so what equation relates pressure, volume, and temperature? Well, we want to solve for volume. But we're given a pressure, we're given a temperature, we're given moles of lithium hydroxide, but we can use that to figure out moles of CO2, which will allow us to solve for volume. So basically we need that equation at some point. But we're given this, we're given temperature, R is a constant. We want to solve for volume, but we're given N indirectly, because we're given N of lithium hydroxide. So basically this is a two-part problem. The first part is, how do you get from moles of lithium hydroxide to moles of CO2? Well, that's stoichiometry. This is a stoichiometry problem. So you have to be able to do chapter 3 material, stoichiometry, or you can't solve this problem. So that's one area where chemistry gets difficult for students, is because you have to know the material on all of the chapters, because sometimes problems cross chapters. And if you don't understand the material in one chapter, you can't solve the problems in another chapter. Okay, so the first thing we have to do is a stoichiometry problem. And then we're going to use what we get out of that to solve for volume. So volume is nRT over P. So since we're given R, T, and P, we have to figure out N. So we got to do the stoichiometry first. Okay, so we have 327 grams of lithium hydroxide. And let's convert that to moles. So how would you convert that to moles? is you have to calculate the molar mass of lithium hydroxide. So 1 mole, so use your periodic table, right? Look up the molar mass of lithium, oxygen, and hydrogen and add them together. So you get 23.948 grams. So now we convert grams to moles. So that would be 13.65 moles of lithium hydroxide. So we have 13.65 moles of this. And now we can convert mole of lithium hydroxide to mole of CO2. Right, using what you know about stoichiometry. So how do you do that? So then you remember, if you're converting from one chemical to another, that's where you use the molar ratio. So it's a 2-to-1 ratio. So 1 mole of CO2 reacts with every 2 moles of LiOH, right, according to the chemical equation. So 1-to-2 ratio. So this is going to react with 6.827 mole of CO2. So now we have N. So now we can use the ideal gas law. Okay, so 6.827 mole of CO2 times R, 0.0821 liter atmosphere per mole Kelvin, times temperature in Kelvin, 298 Kelvin, divided by the pressure. So pressure was 781 millimeters of mercury. Okay, and then we had to do a little bit more work because if you notice, in the ideal gas constant, pressure is given in atmosphere, but here it's in millimeters of mercury, so I need to convert to a common unit. So 1 atmosphere, so you'd have to be given the conversion factors and then know how to use them. So we convert millimeters of mercury to atmosphere, and now all of your units should cancel out, and you should be left with a unit for volume, which is the liter. So Kelvin's going to cancel, right? Moles are going to cancel. Atmosphere on top is going to cancel the atmosphere on bottom. Millimeters of mercury is going to cancel, and the only unit left is liters, which is what you want, so you can be confident that you have the math set up right. Okay, so if you calculate that out, you should get the volume is 160.4 liters of CO2. So 327 grams of lithium hydroxide would react with 160.4 liters of CO2. And now problem is done. Okay, so that's just a few examples of how to use the gas laws. And so you should be able to do similar problems like that on the final exam.